Hey everybody. My name is Zach Musgrave. I'm a software engineer at Yelp. I'm on what's called the infrastructure team at Yelp, which means we build developer tools. We are interested in performance and security and monitoring and pretty graphs and stuff like that. And I'm here today at reInvent to talk to you about a topic near and dear to my heart, which is profiling, code profiling, performance profiling in production, the triple P. This is using a couple different technologies, but what we're going to be talking about is how we analyze web requests, production web requests at scale using MapReduce and Storm. So, give you the quick overview of the talk before we really dive in. First, we're going to talk about why this is important. Why do you care? Why should you profile your code? Why does this matter? Then we're going to talk about how you create and analyze profiles, how you get those profiles out of your web app and into a place where you can then manipulate them, how you can search them and sort them and tag them so that they're useful to you, how you can aggregate your profiles together so that developers do not have to go through thousands of files at a time, talk about how we're going to do this in real time instead of as a batch job, and we're going to talk about where we're going in the future at Yelp with profiling. Let's get started. In a magical world far, far away, apps don't break. They don't slow down. Developers actually think about scalability as a matter of course instead of as an afterthought. All your external services run in 01, and they run in 01 all the time. And you know about all your bugs ahead of time. It's paradise. There's beaches and palm trees. In the world we live in, not so much. Accidents happen. Developers are not Cylons, they are people. Don't forget it. And they make mistakes. And then these mistakes make it to production, and then we cry. So one fateful day, you have a graph. Your graph looks like this. This is a moving average of the 50th percentile of web request response times for a certain page at Yelp, and something went wrong, which results in this. Everyone wants to know who did this. Why did we do this? Why is responses lagging by 25% at the 50th percentile? And how can we fix this quickly? Business Cat says, your performance needs profiling. I don't know how else to break it to you, but it does. So now let's talk about the actual nuts and bolts of profiling. And this talk is entirely based on Python. This is because Yelp is mostly a Python shop, and I know a lot of people in the audience probably use Python for their web apps, so hopefully, even for those of you coming from a Java background, this won't be too off-putting. But I assume some fraction of the audience has dealt with code profiling before, I hope. So if you haven't, the upshot is that profiling is something you do at runtime with any program. It generates deterministic statistics. How many times has a method been called? How long is that method's runtime? What is that method called and where can I find its source? And how much total runtime is devoted to a certain thing over the entire execution of your program? And in Python, it's really easy to use ad hoc. You just run your script with the cprofile module turned on, then it wraps your script and it generates an output data file. This is built into Python. I think in Ubuntu you have to install an apt package, but this is already there for you. Profiling's been around for a while, it's nothing new. And when you get your profiles, you end up looking at something like this. So what you can see here is that, for example, we have a part of our web stack called the emergency CAPTCHA that spends a lot of time calling something called access cookies. And so you can drill down and see, as you go, what each method's expensive part is. And so this is obviously just a very abbreviated part because 1-point font isn't very readable. But as you can see, profiling data is structured. And with structured data, we can do analytics without even having to do all the machine learning bits. So we can diff them. And so in this example, we have a tool called diff-pstats that basically takes two profiles and compares the some attributes in them to the before and the after. And what we can see here is that at Yelp, for example, in the top part, we have a request bucketer. And a couple months ago, the request bucketer wasn't taking up that many calls, but now it's taking up a lot of calls. So that could be interesting if you were trying to figure out why something was slow. Maybe there's something iffy about the request bucketer that's affecting more stuff now. And then down at the bottom, we show based on cumulative amount of runtime between these two profile files. So you see this, and you say, well, that's cool, Zach. I don't know how this is going to help me, though. I have a big website. So you ask, how does this work in production? Everybody say hi to Darius. Darius is our mascot for this talk. He's the profiling hedgehog. He's very nice, and he wants to help you build more performant web applications. So Darius will tell you about how to acquire profiles from your web app. This part's actually sort of simple or sort of not. It really depends on the architecture that you're already working with. But basically, you make a context manager. You wrap your application in it at a reasonably high level, so you're including all the pain points of your application. And sometimes you return a profiling context. You have to have a place to put your profiles. And we use a distributed logging system originally created by Facebook called Scribe. I'm sure some of you are also familiar with Scribe. If you don't use Scribe, or you can use another solution or save them to a local disk, it really doesn't matter as long as they eventually end up in the cloud. In our case, our Scribe logs eventually end up in Amazon S3. And this makes the profiles easy to deal with. You also have to add, if you want to actually be able to figure out which profile goes to what, some sort of a logging stream that contains semantic data about your application. Once you do this, you can then go through the attributes of that logging stream and be like, okay, this profile matches this thing. So for a system diagram, we have the internet. We have two data centers, East Coast, West Coast. This is very idealized. It's a lot more complex in real life. And each data center has one or more Scribe aggregators, which take all these lines of logs from all of the web workers and eventually uploads them to S3. It also allows you to access them in real time to do like log tailing and stuff like that. But once your stuff is in S3, you can then dig into the real details of how you actually analyze it and how you make it usable. So one thing I've noticed about talks at conferences like this is that not everybody includes code in their slides. And it's hard to include code, but I'm going to try. So I hope you'll bear with me, and I'll try to explain as best I can. So here's that context, the context that we were talking about wrapping your web app in. Basically, when you enter the context, all you do is you turn on the C profiler, and you enable it. And when you leave the context, so at the end of your web app's internal execution, you tell the profiler, give me all the stats that you created. And then you create a dictionary, in this case, that has attributes for the actual profiling data and for what, in this example, is called Ranger, which is the logging attribute scheme that I alluded to earlier. At Yelp, this is called Ranger. Yours is probably called something different. So we take our request info and our profiling info, and we use the C-log library to dump them into Scribe. So hopefully that's pretty straightforward. When you enter, you turn on profiling. When you exit, you turn off profiling. You take the stats, you combine the stats with the attributes, and you write it out into whatever logging system du jour you prefer. But it's important to note that profiling isn't free. And maybe this comes as no surprise because you're creating another data file and you're keeping track of all the stuff you normally won't keep track of. But there is an overhead. And anecdotally, it's probably about 20% on your response time. So you don't want to profile all your traffic. Also, you're going to generate a ton of files. So you probably want a context manager to decide whether or not you're going to use the context I just showed you. So maybe you create something, should I profile this? And so you look up the servlet that you're working on, and you say, based on some random probability, either profile it or don't. And then you decide which manager, based on whether that random worked out one way or the other. And if you have it turned on, then you send your profiles to Scribe. And if you don't, you return a no-op context that doesn't actually do anything. So once again, overhead is a thing, and you honestly don't really need to profile all the traffic that you get, but it's important to get something of a normal distribution of a sample. And you should also, while you're at it, since you're already digging into sort of the lower layers of your web application, you may as well think about maintaining a configuration file, because you have a default percentage of requests to profile. At Yelp, this number is very low. It's under 1%. And let's say you have a specific servlet, like your terms of service page. Nobody ever reads that. And hopefully it's pretty static so it doesn't have too many performance problems, but maybe it does. And so if you need to profile that and you want to actually get a decent sample size, you may need to turn up the actual amount of profiles that you're going to create. Like instead of less than 1%, maybe you take 5% or something like that. So we use a Python module called pystaticconf that allows you to read a YAML file, automatically reload the YAML file if you push that configuration change out. And so you can set all this pretty easily. But now let's talk about what you do with all these profiles and how you make them searchable and sortable. Usability is key. I'm a tool builder. My customers are the other engineers at Yelp. They're not the customers who use Yelp every day to find great local businesses. They're actual engineers who also work at the company. But having 150,000 of anything per day is hard. You need to be able to actually search, sort, filter this stuff, and you need to do it quickly, because otherwise it gets stale. If you notice that graph that I showed you earlier and you say, holy crap, my website is 20% slower than it's supposed to be, then you need to fix that yesterday, or at least right now, because you're bleeding performance and probably bleeding traffic, and your customers are getting upset with you because the page is slow. So Darius wants to be fresh and have fresh data, and you should too. And so I'll talk to you about our initial approach on how to do this, which is Amazon's Elastic MapReduce, EMR. And so if you're not familiar, EMR lets you run MapReduce jobs in the cloud. How big a cluster? As big as you want. It spins up on demand, and it's super easy to use with Python. And this is key for our purposes, because all the code I'm going to show you is in Python. Yelp maintains what's called Mr. Job, which is a library allowing you to write MapReduce jobs in Python. Darius and Mr. Job, our mascot here, they're best buddies. They work together all the time. So you want to take these lines of scribe logs that you've been emitting out of your context in your web app and parse them into the correct formats. And you can do this in parallel because each line is independent of one another. They're not related at all. And you can then save those into Amazon S3, one file for the profile, which allows you to keep it in a format that can be analyzed, and one file for the logging data. I believe in our case we use JSON. And you then analyze that data for searchable parameters, which once again you can do in parallel. So it starts to smell like a MapReduce job. You might wonder, what are these parameters, you say? What does Yelp care about? And I have been entrusted with telling you that we are interested in, is the user logged in or not? What page did the user access? Which is split into three things: site, servlet, action. So whether it's our main website or our website for business owners. Which data center? East Coast, West Coast, Best Coast, some other coast. When did this happen, of course? And how did it happen? Was it get, post, put? And were we over or under a 1-second response? Honestly, you can bucket how long on anything that you want. We choose to bucket just on 1 second because it's pretty straightforward, and that's usually sufficient for really bad performance analysis. So let's show some MapReduce code. So this is the beginning of the mapper for the first part of this job. We're going to read in lines of scribe logs that are actually coming out of S3 because Scribe puts them there for us. And the first thing that we do is we process this data into formats that Python understands. So you end up with a dictionary and a pstats object. And then you decide where the hell you're going to put those. So in this case, get base key name just returns a partial path to an S3 bucket. So logs, cprofile, discrete, year, month, day, timestamp, and then a hash. So now that you know where you're going to put them, you can just put them there. So just save them into S3. And you'll notice, for the Pythonistas in the crowd, you'll notice that I'm using the Marshall module here. And everybody says, don't ever use Marshall because it depends on the version of the code that you're running and it's really hard to reproduce. And the reason that we use Marshall here is because pstats, which is related to cprofile, is a really old module and it works best with Marshall. Just take my word on it. This is one of the few times when using Marshall in your own code is okay. And also that my helper function is called setObjectGz. So this just happens to gzip everything before it sends to S3. Also really important because, as you'll see here in a little bit, we generate a ton of data with this pipeline. But anyway, once you've saved out these individual files, you then want to create all the attributes that are important. So we treat these as key/value, data center /SFO, West Coast, logged in /true, servlet /home. And so we create all of these based on the attributes that we've provided from our Ranger line, and we then yield them out. So what this does is it multiplexes these tags from the mapper into many reducers, or one entry in the mapper goes into many reducers. Going on to the reducer, see, the first thing that you see is that we're taking a tag key, like data center /SFO, and then we're taking some paths that match that. First, we have to figure out where we're going to save all our tags. And so it would be conceivable that you'd want to put this stuff in some sort of a database solution. But because this is an internal tool, and it's really, the load on the actual analysis doesn't have to be that high because you're only going to have a handful of engineers using it at once, we found that it's sufficient to just put the tags in files in S3 and then just download the appropriate files when you want to make a search and take an intersection and just be done with it. It's a lot more straightforward and it's persistent and you don't have to worry about stuff failing on you and all the various intricacies of database administration. So we figure out where we're going to put these tags, and there may already be tags there depending on the nature of our runtime. So we're going to pull down the previous object, split it into a list, add on the matching list that we've been provided with, and then write that back out into another string, save that up to the tag file, and then we yield out a debug about how many paths we actually processed in this reducer. So that's the first step. There's really two MapReduce jobs going on here. That's the first one. We took you from having a web app, adding a context, getting profiling data coming out of the web app and into S3, and now you have individual profiles written out into S3 and a record of which ones are which and where they match, all in like 100 lines of Python. So I think that's pretty cool. But now let's talk about aggregating similar profiles together, and on the systems hacking level, this is where things get a little ugly. The fact is that no matter who you are, any single profile doesn't tell the whole story. If you pick a certain file that you happen to, certain profile you happen to save, and you download it and you analyze it, maybe it'll show the bad behavior that you experienced, but maybe it won't. You really don't have a guarantee. So you need a bigger sample size. The problem is that you have a big website and you're generating a lot of profiles, you're going to have to analyze those individual profiles one by one. And no developer wants to do this because they're pressed for time and they want to know why things broke without having to write a big loop or to actually look through them by hand one by one. So we create aggregate profiles. Darius would tell you that it's hard to see the hedgehogs for the trees. But this is one way to combine many trees into one big tree. And so per day, for each set of parameters that we generate, data center, user logged in, servlet name, whatever, we will create a single file for that day of everything that matches that. So then we can see the big picture a little more easily. And that code starts to look a little something like this. We're going to write another MapReduce job. This is all based around the MR job module that Yelp maintains, actually. It's open sourced on GitHub. We're going to read in path names that may match for a certain day, like the entire day's list of path names. And so we're going to download the logging data so that we can analyze that. And then we're going to download the profiling data so that we can work with that and combine it all. And then we're going to generate the key examples: data center, West Coast, user logged in, homepage, servlet. And you look at this and you say, Zach, you already showed me this. Why do I care? Well, the fact is you do care because this turns quickly into combinatorics hell. Because now what we're going to do is we're going to generate every single matching path for all possible sizes of attributes. So if you have 7 attributes total, we're going to generate one that matches all 7. Then we're going to generate more and more and more that match 6, 5, 4. And then everything's going to match the no parameters file. So yeah, that's right. We're taking every profile we generate for a single day and cramming them all into one file. You heard me right. But we do all this, and eventually, for each one of these matches, this turns into a huge multiplex. We emit the path of the file, of the specific file, and we actually emit the path of the aggregate file that we're eventually going to save into, and then we emit the data that we're going to put there. And if you look at this, you notice that there's a method called batch process paths, and it's underlined and it's in green, and that's not fitting with the style that I'm using, and that's because that function is messy. The first version looked a little like that. I'm a recovering Lisp programmer, please don't judge me. But there's an XKCD for everything. Someday Lisp is coming back, mark my words. So, aggregating into multiple requests, let's talk about the reducer. So, given an aggregate path and one or many entries that match that path, I'm going to build an accumulator. It's pretty straightforward. And this code is somewhat reduced from the version that we're actually running in production, mostly for the sake of fitting it on the slides. I reckon that if you go out and you intend to build it, if you started from this, you'd eventually figure out like the little nooks and crannies, which is basically exception handling. So build an accumulator, set everything to none or empty, and then for each entry that you're given for this aggregate profile that you're going to generate, combine the pstats objects into a single pstats object. And this is made easy because that module happens to have an add method. So this is built in from the get-go into the stock pstats. And then, of course, you want to add in your logging data together because this will create a big, long JSON list of dictionaries of attributes. The second part's on the second slide. We now are going to generate the batch path name from the partial key that we were given and save the combined profiles and the combined attributes back into S3 into another location, which is called data cprofile processed. This batch runs. And it's called processed because this stuff can be easily regenerated. Actually, if you keep your scribe logs forever in S3, either one of these can be easily regenerated, but this one in particular, we already have the raw individual profiles, so we can go back and run through this whenever we want. And then once again, yield out a diagnostic about how many lines we actually created and saved. Going back to the system diagram end of the spectrum, we start with a web request, profile me maybe, and it goes to a scribe aggregator. There's a first elastic MapReduce job, which is when we upload them into individual profiles and tag them. So we get discrete profiles and logs and per attribute tags. And then there's a second MapReduce job that aggregates them into combined profiles, which then writes those out, of course, into S3 again as the combined profiles. You'll notice that there's, in the top right, there's the profilistic service. And this is where Darius hangs out. And this is basically a quick and dirty web app. Nothing too special from the web app construction end of things. But profilistic exposes the collected profiles, in a relatively easy to use interface. Profilistic will also allow you to start up ad hoc combination MapReduce jobs. So we, by default, only create files for a single day. But let's say that you had a servlet and you wanted to know all the long-running profiles for that servlet over a week. Well, we don't do that by default. But Profilistic can do that for you, and so all you do is provide Profilistic with your email address, and we'll run an ad hoc job, and you'll get an email notification when it's complete. This actually doesn't really take very long because at the front end, we can filter out all the records that don't match ahead of time. So now here's what I'm going to tell you. We have, for every possible combination, a combined set of profile statistics and a combined set of logging data. For example, if you were debugging the biz details servlet, which on Yelp is when you actually see the photo of the business and the hours and the recommended reviews and all of that, it's one of our big important pages, as you might expect. So biz details slowed down for some users, and we start out thinking, long running is bad, of course, and a lot of times there's extra stuff that's added to the page when the user is logged in. So as a shot in the dark, let's turn those two on. And you get your profiles, and you notice, a higher percentage of these are bad compared to the everything biz details ever for that day, but some of them are still okay. So then you think, maybe something's gone wrong in our East Coast data center. So you filter by that, and now you see, okay, I have a higher still percentage of bad stuff. And then you say, maybe it was only post requests, like writes to the database, maybe. So you do that, and then you realize that this problem is only defined to the main World Wide website, the www. It doesn't happen on the mobile, doesn't happen on APIs, anything like that. And so now we have gone from knowing one parameter to knowing 5, and at this point, everything looks terrible. And so now you have something to go off of because you have some idea of where this behavior has come from. And now you can go dig into the profiles with a lot more knowledge and assurance that you have something to go on. Going back to this, we can see that diffing to pstats from several months ago and from now, once you've narrowed it down that much, makes a lot more sense. So if you had one line in this file that, for example, had a before of 200 calls and now has 20,000 calls, you know what happened. Somebody didn't optimize something, and it's being done several orders of magnitude too much. And so you can then probably go and isolate that method and git blame it and find that person and talk to them about why is this, can we do this better? It's not working out for us. But just like every good thing, every nice hedgehog, rent needs to be paid for the hedgehog, right? And at least the way we do it now, rent on profiling at Yelp isn't cheap. These are per day. We generate, on this day, and this number is actually a little outdated, on this day we profiled 152,000 and change discrete web requests. We created 40,500 aggregate combinations from no attributes to all 7 attributes turned on, which created a total of 386,707 new files in Amazon S3. Luckily, we gzipped them because even when they're gzipped, they take 62 gigs a day. Oh, and we don't delete anything ever. So there's that, right? Storage is a problem. Of course, you could very easily, if you decided that maybe you didn't care about your profiles from a year ago, because your app has changed so very much from a year ago, you could just create a cron job that goes out and deletes all that stuff. That's up to you. There are many ways to keep your storage down, and none of them are particularly technically interesting. But performance is another problem. So I suspect for a lot of people in the audience, the last time you saw a cumulative distribution function was perhaps in graduate school. And this one describes the profile count per aggregate file. And that's a really long tail. I'll break it down for you. In MapReduce, we assume, we hope, we pray that every unit of work that we do every mapper, every reducer is going to take an equal amount of time, more or less. But for profiling, because of this combinatorics hell we've got ourselves into, that's just not true. So 60% of the files we generate contain 10 or fewer profiles, and they generate almost instantly. You're just bound by the network gap between your Elastic MapReduce cluster and the S3 endpoint that you're accessing. So 60% easy. Even 95% isn't so bad. 95% of them contain 1,000 or fewer profiles, not so bad. But there are 8 files that we generate every day that contain over 100,000 profiles. You can probably imagine what some of those are, like the one that contains everything, for example, is the big offender. Of course, you could just decide, well, for these big sets, I don't even need to generate them. Like, why do I care? I'll just skip doing those. And sure, that's fine, except we found that our engineers are actually particularly interested in those big sets, and every attempt to stop doing them has led to people saying, these are useful to me, please find a way to keep them. So we've kept them. But you remember Darius? You remember how I was talking about this should be easy to use? Well, it's his time to shine, and we'll talk about the actual little web app. It's called Profilistic, and it looks like this. Pretty straightforward interface, nothing too pretty, functional. But you can select a beginning date and an ending date, how many records you want to include. If you'd like your job to run a little faster and you're asking for 1 million profiles, you can downsample to 1,000 if you want. Whether or not the job's long running, whether or not the user's logged in, which data center, which HTTP method. You can select multiple of these if you want. Which of our internal sites, whether www or mobile or whatever, and the servlet and the action. And if you specify your email address, then you can start an ad hoc job and get an email when it's completed for over multiple days of records. But normally, people are interested in one day. This is probably 80% of the use cases for Profilistic. People are interested in one day at a time. And so that stuff's generated every night. So we just say, hey, this data has been created and cached for you. And so in this case, on October 1, we processed 28,000 profiles for the business details page. And so you can just go and download those combined files. If you ask for something that, let's say you ask for a month of profiling data across the entire site, you're probably going to be in trouble because that's going to be, that job is going to take like a week, 2 weeks to run with the normal cluster size. So for this guy, for example, automatically condensed it down to 1,000 of the choicest, juiciest profiles, and by that I mean a regular stepwise sampling. But it makes it a lot simpler, and it makes the user happy because instead of having to wait 6 hours or something for this relatively small, by default, EMR cluster to run their job, this takes about 15 minutes if we downsample to 1,000. And most of that 15 minutes is bootstrapping anyway into setting up our pipeline in Elastic MapReduce. There's also the email that you get if you ask for one of these ad hoc jobs. So in this one, we asked for 1,000, and there's an off by 1 error, so they got 1,005. But I think they'll be okay with that. I know a lot of people have been interested in this talk because of its applications to real-time data processing, or its use of it, and how Yelp uses Storm. So let's talk about real-time. If you're not familiar, Apache Storm is a real-time distributed computation platform. And basically, it's a directed graph of processing steps. And so it passes around tuples between individual parts of its topology, since it's a graph. So you have spouts, which are sources of data. So scribe has a spout, for example. You have bolts, which are processors of data. So just like a mapper or a reducer in our Mr. Job code that we went over, you can see how the parallels might lie there. And then you can set up groupings, which define how tuples move between individual spouts and bolts. But Apache Storm doesn't support Python out of the box, so we did that for you. We just recently released, open sourced, something called Pyleus, which is a Python framework for Storm topologies. It's super, super new. This was like literally a couple weeks ago, and it allows you to build storm topologies in pure Python. They seriously don't look hardly any different from the MapReduce jobs that we showed earlier. It also has this cool feature where you describe its structure as a YAML file, and it'll even respect a requirements.txt. So if you have pre-packaged spouts and bolts, you can just hook them together based on the fact that you have the packages and just hit run and it just works. So I'll show you a sample Pyleus topology. This is the beginning of the one for Profilistic. We have 3 workers set up. This was a test cluster, I believe, at the time. And we provide 2 spouts. We provide a West Coast spout that reads out of the West Coast data center and reads out of the C profile stream coming out of Scribe. And we provide an East Coast one. These are idealized, obviously. So West Coast and East Coast data center Scribe spouts. You also provide the bolts. So the first one is basically equivalent to the first mapper in the first MapReduce job. All it does is reads out of the Scribe channel and processes the profiling data and the logging data and sends them out to S3, and then passes onward all the tags that match it. So you see the shuffle grouping because what we're doing is we're merging data from the 2 data centers together. The second bolt, similar. It's pretty much the equivalent of the first reducer, but we also include an S3 cache. And what I mean by S3 cache is when we're going to receive profiles in real time that match a certain set of attributes. West Coast data center business details user logged in, for example. And so this one particular bolt is going to process all of these, but since they're coming in continuously, we probably don't want to hit S3, given that it's eventually consistent, every time we get a new record, because for some of these really heavily utilized bolts, that's going to create a lot of trouble. So instead, maybe every 5 minutes, you accumulate this stuff for 5 minutes, and then after 5 minutes, you write it out to S3 and reset your accumulator. And in this case, you notice that we set what's called a fields grouping. And the fields grouping is based on the tag. So like I said, the however many attributes that we're going to combine upon. We'll go on from here, and I'll show you kind of the basic Pyleus structure. My first bolt, based upon simple bolt. Set up an initializer if you have a configuration file. This runs, on startup. Set up your S3 bucket if you want to do that. And then you just process the incoming tuple. You get a key and you get a value, and then you do stuff here and create your new tuple and emit it. And give it a name equals main, and you're done. That's a Pyleus bolt. It's pretty straightforward when you take all the logic out of it. So, Profilistic and Pyleus, for our specific application, the profiles used to be 1 day delayed. And what I mean by that is, for profiles that were collected on a Monday, based on Monday's web traffic, we'd make it to about 1 a.m. into Tuesday, and then we'd kick off our batch jobs. So the batch jobs would take, in the cluster size that we were providing them with, the first one was a little under an hour, and then the second one was somewhere between 2 and 4 hours. So by the time our engineers on the West Coast came into work, the profiles for the previous day were already there. So that's fine, but in emergencies, that's not fine. If it's 2 p.m. and crap hit the fan at 10 a.m., you wouldn't normally get those profiles until the next day. So in that case, usually somebody would come to me and they'd say, please start the batch ad hoc, we really need the help. But because we have this running in Pyleus and Storm now, at 10 minutes or so after bad performance, you just get your profiles. You just get them now, they're there for you, you can investigate whatever's wrong with your application. This has made a lot of engineers very happy, and it's made me happy because people have stopped bothering me to get me to turn on the batch jobs. So, talk a little bit about the future work and ideas and stuff that Yelp has in mind for profiling. And for one thing, I actually have an intern working on this right now, active monitoring. Since we're already creating these big sets of profiles, and we're already doing it in a storm topology, for every new aggregation created each day, Just pull the same combination from a day, a week, a month ago, whatever you want, diff them. And if you see a bunch of really bad performance indications, alert somebody, send an email, ticket this in your tracking system, whatever. Because you already have this topology, and you're doing a diff, so there's two things, and half your data's already there. Half of it you're getting for free at the end of your last bolt. Instead of just saving it out to S3 and being done with your life, you emit it one more time and it goes on to the next bolt and you do your alerting checks. Second one, visualization within the web app. We already had a script that would parse our profiling data and convert them via GraphViz to PDF. But in our most recent Yelp hackathon, which was just a couple weeks ago, somebody actually built this. So my slides are a little out of date, I apologize. But now you can just select a profile and in the web app just say, boom, here's the call graph. See everything, see the percentages. It's great. So hopefully I haven't thrown too much information at you. Getting a little low on time. But you might wonder, what are the takeaways of this talk? I've talked a lot about a couple different things. So I'll give you the upshot. Step 1, wrap your web app in a context manager. Step 2, take data from that context manager, send it, these profiles and logs, into the cloud. Step 3, tag these with the attributes that you care about, whether that's the data center, whether that's a specific logged in user, whatever works for your use case. Step 4, take all of these attributes and do an all pairs combination. Make a single file for any possible use case of terribleness that you could have. This prevents an engineer from being faced with 500, 5,000, 50,000 files and not knowing what to do with them. Build a quick and dirty internal app to be able to access this stuff easily. This should take, a lot of people in the audience like half a day. And then if you want it to be fast and you want it to be in real time, you can refactor it into Storm and Pileus. And at the end, make sure you give Darius a hug because a lot of people get upset with him when he doesn't work and he could use the love. He believes in you. Real quick, Yelp's dataset challenge. If you've been interested in some of the datasets that Yelp collects, this is an academic-oriented dataset from 5 cities, and it contains over 1 million reviews, over 250,000 users, a social graph, a lot of interesting information for academic use, research, visualizations, submissions by the end of the year. There's more details online, yelp.com/datasetchallenge. And thank you all so much for coming out to the talk. I'll be outside after this. You can reach me, ZTM, my initials, ZTM at yelp.com. And you can find out more about the MapReduce and Storm packages to do them in Python. These are Mr. Job and Pileus at mrjob.org and pileus.org. So thank you so much, and it looks like that is about it.